Hello everybody, Mr. Hasty here again. Today we're going to continue our chapter on sound, discussing the properties of sound. So the first topic we're going to discuss is intensity. And when we think of intensity, we tie that in our perception of sound to loudness, but they are slightly different in how they're distinguished. So, what does intensity mean? It means the amount of energy that passes through a certain area over time. So intensity really means how much energy there is. So an easy example of this is the control knob or the volume knob on a stereo. As you increase the volume, what you're really doing is increasing the energy of the system. Increasing the electrical energy increases the wave energy, and you have more energy going through the space at the same time. And we'll perceive that as being louder. Now, visually we can look at it as a higher intensity tends to have a higher amplitude. Now, when we look at transverse waves, we can compare them here. We have a high amplitude wave and a low amplitude wave. The low amplitude wave just doesn't get up as high or go down as low. From its baseline, it doesn't move as far off. That'd be a low intensity, whereas this would be a high intensity. But sound waves aren't transverse, they're longitudinal. So these are air particles in these two examples, and the higher amplitudes, the higher intensity, creates stronger bands, stronger compressions, and deeper rarefactions compared to the lower amplitude wave. And this explains a couple phenomena that we understand with sound. So if we think of these sound particles as moving, as they move through air, they're going to disperse the energy. That's why something can be loud close up, but as you're far away, it's quieter, because the energy dissipates as it goes on, just like friction or other types of dissipation resistance. As energy transfers, it tends to decrease over time. The second thing is, if you get a loud enough sound, you can actually feel it. And that's because what sound is it's air pressure waves. And when that pressure gets high enough to where you can actually feel it with your nerves, with your skin, the sensors you have built into your body, that way it's something like you experience with very loud sounds. So let's talk about loudness as opposed to intensity. So this is the perception of increased volume. Now, there's a couple things that affect the perceived loudness and why it's not the same thing as intensity. If you increase intensity, it tends to feel louder, but also if you change pitches in a certain way, it can tend to seem louder. Distance affects how we perceive loudness and other factors as well. So loudness is not purely intensity, but they are very, very closely related. All right, let's talk about how we measure the loudness and intensity of sound waves. So we measure loudness on something called a decibel scale. A decibel's abbreviation, it's a unit of measurement, is dB. And it's our base unit of sound intensity. So this scale doesn't work like other scales you've experienced. The way a decibel scale works is every increase of 10 is actually 10 times. So it's very strange. There's not very many scales, probably none that you've dealt with that work like this. So adding 10 decibels really means that you're multiplying by 10, the actual intensity of the sound. So if you added 20 decibels, that's not multiplying by 20, that's multiplying by 100. That's multiplying by 10 and then doing it again, which is the same as multiplying by 100. And if you go up by 30, that's 1,000. So there's actually a very large scale, if we just go straight numbers, of how quiet they are. But to give you some ideas, whispering is about at the 10 decibel level. I'm sorry, probably more like 20. Somewhere in the 10 to 20 range would be whispering. 50 is an audible noise where you're going to be noticing it quite a bit. The example the book is a running air conditioner, something that makes a background noise. When you're inside of a car, the noise of the car itself. Someplace that's loud, like friend's house, something like that. The cafeteria, that'd be about 80 decibels. Concerts, we talk about loud music, loud concerts, about 110. So loud music is about 110. And our pain threshold is 120. That's where humans start to experience pain typically. And to give you an example, jet is at the 150 mark. Like a jet, if you were to just listen to a jet taking off. So anything around this range, anything where you start to get past 100, you really want to be wearing ear protection for to help reduce the damage. Now, how does it damage your body? Well, the way it works is, we talked about this before, you have an ear, pardon my poor drawing, and that goes into an ear canal, which hits a eardrum. When the sound waves go in there, the intensities you can think of as the force that they hit your eardrum with. And if they hit your eardrum in a hard fashion, that can cause damage both to the eardrum and what's inside of there as well as it transfers. And so that's kind of why we want to wear ear protection past some point. And it's really important past that like 100 decibel range. All right. So pitch. Pitch is how high or low a sound seems to be. Now, this is related to the frequency and thus the wavelength of the sound. So if you have a high frequency sound, we perceive that as a high pitch sound. And a low frequency sound is a low pitch sound. So real quick, for those of you who aren't familiar with pitch, you're not in music or something like that where you experience that. Let's just give it real quick. I'm going to use a virtual piano. So low pitch, low frequency. High pitch is high frequency. So low pitches have a low frequency, high pitches have a high frequency. Humans have a range of frequencies we can hear, typically between 20 to 20,000 hertz is what we can hear. But that's just the human perspective. Dogs can hear up to 35,000 and bats can hear up to 100,000. So our range is pretty good, but it's nothing compared to some other animals. Now, one thing that's interesting about frequency and pitch, and we'll talk about this more in the section of music, is certain pitches, because of how they line up together, and I mean how their waves actually line up, sound nicer than others when put together. So if we play these two notes together, they sound nicer than these. Right? And that's based on how the pitches line up. And this is actually how musical chords are put together. Common musical chord is the first, third, and fifth note. Right? But if we mess with one of those, it can still sound good, but it gets a different quality to it. We'll talk more about that when we talk about music. All right. So now we're going to look at something called the Doppler effect. The Doppler effect is a change in the frequency. Remember, we perceive frequency as pitch of a wave due to motion. So I'm going to try to draw this, and I'm going to have to go through this process twice. So we're going to have a before and after picture here. In both situations, the person who is perceiving the sound is going to be standing on the right side. Now, let's talk about this. Things move and generate sound, and typically they do not move faster than sound does. You can hear a car coming, for instance. If something does move faster than sound, it's said to be traveling at Mach speeds. And that's what we talk about a Mach 2 jet or a Mach 3 jet. Things that actually travel faster than the speed of sound. So let's say that an object's approaching maybe a car. And if you've ever listened to a car pass moving quickly, the tone that the car has when it's coming towards you is different than the tone when the car is going away from you. So that car that's coming towards you emanates a sound wave. We'll call that wave A. But as the car actually gets towards you, it's still headed that way. That wave A started back here. So at this point, wave A is bigger. It has expanded out from that circle. But this car is still making waves. Now there's wave B. And because these waves are crunched closer together than they normally be, you perceive that as a higher frequency. And the same is true if this were going in reverse. If you're standing next to the point where the car is leaving, so this car is traveling this way and it makes a wave, we'll call that wave C. By the time it gets far away from you, still going that way, that C wave has expanded out, still centered right here. Let's try to actually draw that. Okay, that's wave C. And then this wave, which we'll call D, is going to arrive much, much, much later. Now, this phenomenon is not just true of sound waves, it's true of light waves as well. And astronomers actually use this to tell if something that they see in a telescope is moving away from the Earth or towards the Earth. And they do this by looking for changes in color. Things that they would normally perceive as a certain color might go a little bit closer towards the red side of the spectrum or the blue side of the spectrum, depending on if they're moving towards Earth or away from it. And all these are examples of the Doppler effect. All right, guys. That's it for today. See you next time.